Alright, welcome back to our continuation of integrals. And now we move over to our definite integral, which is very much in the first stages. These first few pages would be considered an analysis type idea. It's not coming out very well, is it? Is that up? So it's an analysis idea. In our geometry, we tend to be able to do regular shapes fairly well. So a square might be denoted by having equal sides at 90 degrees all around. And the area of the rectangle would be the length of the side. So if this was a side S, the area would be equal to S squared. And so that would be a reasonable thing to do. Likewise for a triangle. A triangle would have an area, and if we drop down a height here and denoted that height, and it was a bisector, so it's 90 degrees, then we would get that the base is the width of the base of the triangle. Then we would get that the area would be equal to half the base times the height, as an example of a generic geometric type expression, half the base times the height. Even for a rectangle, we could have breadth, length times breadth, breadth times width, length times width, height, if you like, and the width, breadth, and the area of the rectangle would be that just the breadth of the thing times its height. Very straightforward. Even for more advanced ideas, the idea of the area of a circle, actually prove this in Maths 2 at some point when you're doing a particular work there, and that radius, the area of this particular part, the internal area, is equal to pi r squared. So we're very good when it comes to standard geometries of working out areas. So what about when the areas aren't just a standard geometry? What about when they're a bit more complicated? So it would be helpful, wouldn't it not, to have an area that is related to irregular shapes. So irregular shapes would be helpful, and I guess that's what we're looking for, irregular shapes. So I have a little bit of a think about how we might go in defining irregular shapes. And so what we've got is our function value, y equals f of x. And then we've got our x as usual. And in this particular case, what we'll do is we'll say, well, how about we set up an a, x equals a, and x equals b. How might we go about estimating the area under this curve? That's an unusual geometry. one of the sides is very irregular, and so as an irregular geometrical figure, we have a little problem. So how would we go about doing that? So one of the things that we can do is consider looking at estimating or approximating. I want to be careful in using that word because in the mathematical sciences that has a particular meaning. Approximating the shape, if you will, of this particular curve. So we can think about this curve in terms of a number of different ideas. Some of the ideas for estimation might be simply in your A-B space, thinking about maybe we could just use a rectangle. Would that be okay? Let's just estimate this thing up to some certain value, and we've got a length and we've got a height. In other words, we've got a width, breadth, and a height, and we can specify the area by looking at all of the space inside that one, which would be b minus a times, that would give you your breadth, the height, and the function value that's taken on there, the function value minus 0. So surely that would be a reasonable approximation. Well, what's reasonable? Well, we can do better than that. Of course, what I hear you say is, well, we can change the nature of the triangle attack that we use, and clearly we've got some errors, we've got some bits. We'd expect this one here to be perhaps a little bit, well, I'm guessing that area and that area could be very close. So what's the error? What's the percentage error? Well, can we do better in terms of maximising it? Possibly we could think about taking two triangles. And taking two triangles, we could estimate an A and a B, and perhaps we could do two triangles. We could do a lower triangle, let's say a green one, and just pick a lower value. We know that all of the space in there looks pretty good, it's just a regular shape. And then we could pick a higher triangle, a rectangle, up to maybe this value. Okay, and maybe the difference between a superimposed red triangle and a green value would be what's in here. We could add that. So maybe that helps to minimize the error. Perhaps there's another alternative that we could think about. We could think about doing rectangles in a different way. Instead of stacking them like that, you could think about having them go in pairs. So maybe we can do halves and work out the areas. Or maybe we can do halves again and work out the individual areas and add them all up. Perhaps we could go halves again. So at what point can we think about changing the area? And each of these triangles, if we did underneath, okay, underneath triangles, and adding them all up. Then perhaps you could do over triangles where they go up and over, up and over. So we'd have this kind of red and blue contrast again, where the error is just somewhere in there. Maybe we could subtract the two sets and just get a bit of an error. Generally, it seems that what we could do is expand this idea a bit further. So let's have a look at this idea a bit more. I think the stacking of the rectangles was probably a good try, but this dividing up the intervals seems to be an idea that is noteworthy. So if we've got our interval A and our interval B, it seems to me that we can divide up a particular interval and we can name that as a sub-interval. So we've got our outside interval between A and B, and then we've got a sub-interval. Now, perhaps we can think about the area of the sub-interval in terms of the function value and the various values. So if I put this as some value xi and the previous interval would be xi minus 1. And then we have corresponding function values. We would have function value at xi, and then we would have function value at xi, the previous one, minus 1. So that would be that one, and that would be that one. So in doing that this way, we get a sense of a subinterval and a calculation using these two sets of information. So it would be reasonable, would it not, to say that the area, or the incremental area, and the subinterval area, might well be approximation of the function value at xi minus the function value at xi minus 1 which would represent height times the width of the subinterval, which would be the greater of the two x values at xi, subtracting the smaller one. So that product would give us an approximation to the area. Okay. Now if we turned around and generalised this and said all such areas, all such areas could be expressed by this notion that if we incrementalise in subintervals partition and represent the difference in the partition for all such intervals with an asterisk, all such partitions multiplied by the subinterval minus the previous width, which is I minus 1, then what we'll get is an area. Okay, so we want to formalise this a little bit more because what we're suggesting is that this width can decrease. Okay, what about if we use our knowledge, our understanding of this notion of decreasing the subinterval? To what extent does it decrease the width? To what extent does it decrease? Well, we can be imaginative and we can use our human characteristics and we can say that this distance becomes infinitesimally small. Infinitely small. So if it's getting infinitely small, then essentially what we're going to end up with is a very narrow rectangle that looks like a line with an infinitely small width. Okay, xi and xi, the previous one. So that tells us that this is like our idea of when the denominator is 0. How do we avoid that? Well, we have an insurance policy. So the same kind of idea is going to apply here. We're going to have a limit. Okay? So if we have many such rectangles, infinitely small, filling up the gap there, and so on and so forth, all the way to A and B, then we're going to have an approximation for the area that looks something like this. All of the small areas summed together, the width of a pencil, the width of a hair, the atoms are nearly touching, the atoms are not touching, and so on and so forth. Like that abstraction. Okay, that abstraction. N times, we can sum them up. Okay? So the formal limit of this, the formal idea of this, is that we have the area is equal to the sum from I equals 1 to n for all such areas. Okay? And more formally, we can sum this from I equals 1 to n for the aforementioned function values at the subinterval, denoted by the asterisk, multiplied by this ever decreasing subinterval, depending on what we decide on. So the height times the width, or the breadth, will go towards our area. So the area is in fact formally known as a Riemann sum. And so what we get is the area is a limit, and this is our insurance policy, so that such that n approaches infinity, we get an infinitely small variation. And so we get this idea that that will come to some value. And this is called the limit of Riemann sums. Which is in itself is an analysis topic. And I think I made the point in the workshop that in analysis you would spend 5 weeks or so learning about the techniques that are required to get you to understanding the limit of Riemann sums as an analysis idea. Okay, so it's quite an advanced idea in that regard. If I show you this in practice for a particular point of view, then I'll just do this one. No, sorry, I'm just getting a file open to show you. And I'll just bring that file over when I've got it to the size that I want. And I've put this particular graphic up somewhere, but I've just not found it at the moment. But it came from this file, so what we'll do is we'll have a look at this. And what we can think about is sharing this over here. and showing, worry about the more advanced one. But you can see what's happening. Actually, put that up there. It's getting okay. So we can see this graphic is changing. It's not necessary for us to know about those, but sorry, I'm just not getting it where I want it. And I'll have to get that graphic sorted out again because it'll be no end. We can see them changing this. Don't worry about this 3D one. I want to focus on this one up here. We can see that the widths of the rectangles are changing, and so that gives rise to changing intervals. So the limit of the sum is what we wanted to see, and this can be expressed formally. And so the formal expression of that we can give as the area is equal to a limit as n approaches infinity. So there's our insurance policy of the sum of I equals 1 to n for our height value at xi, and we formally call that dx. That's the increment interval. Okay, we call that dx. So what we're about is demonstrating a representation of an area using an irregular shape, using the Riemann sum. So it's a little bit of work, but clearly that's the thing that we want. Now this is formalised in what's called the fundamental theorem of calculus, and the fundamental theorem of calculus is given here. And so this is a big deal. The idea of these parts is that this was something that was developed using analysis techniques hundreds of years ago, and so it represents for us a clearer understanding of an infinitesimally small increment, dx, and so the fundamental theorem has been applied. Now we don't study this type of integral in this subject, and in fact you won't study it unless you do an analysis subject, but it is presented in this way in various textbooks and the like, the proof of which we would work up to over a period of 6 weeks or so. So it's quite advanced in that sense. Part 2 of the fundamental theorem gives us these antiderivatives that we want to use, and so we go about setting up all of these bits and pieces, and we understand that the definite integral is a number, and it's derived from a lower limit and an upper limit. So we will learn how to use those in the next video. So let's just pause there, and I'll be back soon.